actually going to be talking a little bit about embeddings and about pre-training your own embeddings. This is going to be very practical in terms of its approach. And it's sort of the talk that I would have loved to have heard about a year ago. And so I'm going to be talking a lot more about the practice than a lot of the math behind the embeddings. And I'm specifically going to be talking about exponential family embeddings, which are a method that was developed by a lab actually here at Columbia, David Blei's lab, and how we found them to be actually an interesting set of algorithms and models for the sort of questions that we have to ask. And I think that they have a lot of very interesting potentials for industrial applications, so things for like recommendation systems and things like that. But a bit of background about us. So we are a startup, and we're based sort of in the human resources area, and we're specifically right now focused on looking at job descriptions and helping employers write much better job descriptions that attract a broad candidate pool. And so we do this through three major mechanisms. And so we're essentially, the idea behind our mission is to sort of bring data into people analytics. And the first major mechanism and the first product that we've commercialized is a smart editor for job descriptions, which I'll show you on the next slide. And essentially what it does is it breaks down a job description into the language, into the skills that it's talking about, and tries to make suggestions based on what we know works in terms of attracting different types of job seekers, and what we know that doesn't work that seems to act as barriers to candidates. The second major mechanism we have is a pipeline health monitoring, which is an analytics dashboard. And essentially what that does is it looks through your talent pipeline and tries to identify areas where you might be not acting very fairly, and there's a bit of bias creeping in. And the third area is in terms of salary estimation. And essentially salary estimation is our sort of one of the many levers that we pull on people who are writing job descriptions to not ask for unicorn candidates. So if we are asking for someone who's a star data engineer and a star data scientist and a star machine learning engineer, and we would estimate that that salary is something like $300,000, usually an employer is going to back off and be like, actually my budget is probably close to 100. And so it's one of the many levers we sort of use to talk about that. So what's underpinned by this is a whole lot of data on job descriptions. We have millions of salaries which we've broken down by skills and requirements. And essentially, it sort of all works in this context. So this sort of gives you a visual of the front of the interaction that you have. We have obviously very specific language and content suggestions. And so this is, we're essentially very much a very strong natural language processing tool, which uses a lot of AI and behavioral science on our back end. And okay, what can I talk about next? So what I find really fascinating about job descriptions is that the importance of language in job descriptions, and we're very interested in how that language plays out in terms of outcomes. But a lot of what I find interesting is that a lot of the current thinking in terms of job descriptions tends to take one or two aspects of a job description and impute things. So in a lot of algorithms look at the title of a job and consider that the most important component. And when you look at these jobs and you break down the skills and the requirements, what you find is that these are actually quite different jobs. A finance manager at a sort of consumer production, CPG, consumer produced groups company, is very different to one which is obviously something more of a finance skill rather than someone who is much more in a sort of more junior role. And the same thing can happen, and this sort of underpins a lot of our work, is that we're able to, by being able to convert that sort of unstructured natural language data into specific skills, we're able to find apples to apples comparisons between jobs that if you look at the titles or if you look at other aspects of them, they're not very obviously comparable. And we're able to do this not only in terms of skills, but to sort of compute things like, even if a job doesn't mention SQL, we can extract that, a relational database experience is likely to imply that. And we do this through a wide variety of different NLP tools. And so understanding and extracting skills and content and requirements from jobs is actually a very interesting, for me, area, because it allows us to, in comparing these two jobs, allows us to get a lot more signal to noise in all of the predictions that we make. So the question that is the sort of focus of the topic today is that I'm going to present to you guys of some of the research that we do is how have data science skills changed over time. And what we're talking about time is from 2016 to 2018 because sidebar, our company pivoted in 2018 or 2017, and in 2016 we were a job search site for 2 years. And so we've been amassing hundreds of millions of job descriptions, and so this is something that we've always been very curious about. So I have a very large proprietary data set of job descriptions. So there are a couple of different mechanisms that we can use to identify changes within data sets, and these are sort of very broad ones, and they're sort of a little historic, and they're getting to the newer point. The first is manual feature extraction, and these are things that I'm sure you're all familiar with. These are rule-based, usually deterministic mechanisms. You can find a whole lot of different ways of talking about SQL and writing alternative ways of extracting SQL or relational database experience. And what the problem with this sort of method is that it requires you to select ahead of time what are the key attributes, and so and to identify all the different ways it's actually spoken about in your corpus. And so it's actually very difficult to identify new attributes or upcoming attributes. What you can do really well with something like this is to figure out things that you know are are important that may be waning in sort of importance, but it's not so good for finding what are the new cutting edge technologies. A more recent sort of mechanism or a more recent alternative are things like dynamic topic models. So these are things that basically convert a document into a bunch of bag of words, and so each document is represented by a whole set of words, and then we look at how they fit into different models and how those models change over time. And again, David Blei's lab, who I'm going to be referring to a little bit later, David Blei himself as a postdoc, I think, generated these sorts of topic modeling and applied it to a bunch of scientific and various other forms of corpuses of abstracts, and to see how, like, you know, the atomic physics has changed over time. One of the difficulties is, for me, I'm sort of new at looking at atomic physics. That's not my background. And if I look at this set of list of words, or even the top 20 list of words, I can't really extract what they talk about in terms of these models and the ebb and flow of their specificity. So it does require a little bit of intervention in a way that requires a lot of sort of knowledge. So let's talk about word embedding. Word embeddings are sort of the third approach that we're going to talk about. And I'm specifically going to talk about dynamic word embeddings, but I wanted to get everyone up on the same place in terms of word embeddings. And so word embeddings are essentially a distributional representation of the meaning of words in the context of their neighbors. And so what we see here is, for example, if we wanted to understand a little bit about Python, and these are sort of some example requirements from typical job descriptions, what we would see is that we would take the word Python and then look at its neighbors in terms of the context of the words around it, right? And these are actually, and so that's what we would do for a word embedding model. And then we'd have sort of, as in going through this process, we'd have a whole bunch of words that would come up here in terms of their proximity to Python and how often they happened. So again, what this abstracts away or converts into is it takes a distribution of words relative to their neighbors and then creates distances. So the closer you are, the more co-localized or more close you are usually in terms of these terms, and the further you are, the less sort of similar you are. And then if we sort of add a broader corpus and consider languages that, you know, other sorts of languages, what we see is something like language gets moved across, and we have those sorts of things. And these have been really, embeddings have been extraordinary in terms of what they've been able to achieve in terms of capturing, for example, entity relationships between words in different axes. And so you can see that this is a representation of a bunch of companies, of Fortune 500 companies and their CEOs. And what I think is fascinating is, although the CEOs are very strongly clustered, the companies, you know, you've got the media companies clustering together, and you've got the non-media companies clustering together, and this is part of a bigger data set from the Stanford NLP Glove project. We understand these in terms of superlatives and comparatives, and so you can understand the meaning if you didn't understand what the meaning of strong, stronger, and strongest was, but you did understand this, you can sort of interpret that, or you could theoretically impute from knowing this what the words are that work in that same dimension. And then the last thing is, and this is probably what's taken people most by the imagination, is this idea that by using these relationships we can impute unknown sort of entities. Or entities that we can impute an entity that we're not super aware of. And so what typically happens though from these sorts of processes, and what's made this actually a really impressive and very powerful technique, is that that we're able to, so from going from corpus generation to final application, we've got a whole bunch of pre-trained models. And the pre-trained embedding models basically cut you through this whole process, and they're ready to go right now, and you can basically put them into your final application. And so you don't have to go through these long-winded processes of corpus generation, of processing, language model generation. What I wanted to highlight, though, is that choosing which embedding model is something that you should do with a lot of care. And I have experimented with all of these different types of models. And what I will say is that, thinking about your final application is very important. Picking a word embedding model, for example, Wikipedia or Google News, which is a little less sentiment focused, and using it on a sentiment analysis application is not going to lead to very good results, versus something like the Common Crawl, which is going to be a lot more sentiment focused. And the other thing that I think is very important is I have great respect for the word2vec, pre-trained embeddings, but I've actually found it very difficult to reproduce those same results, and there is a lot of instability, or you can call it all sorts of things with these models if you're going to train them from scratch using their exact conditions. And so so there is a bit of stochasticity in these. Glove less so, because it's not it's not neural focused in the same way. The other thing that I highlight with these pre-trained models is, particularly with the Glove ones, they have versions that are cased and uncased. And this is actually important for our application, right? It is a common stop word that you frequently find in most stop word lists, right? And so you remove it because you're like, these stop words happen too often and they mess up meaning and things like that. But in our case, what we find is, if you uncase it, so if you have it, if you case it, we have IT. IT is actually really important for someone who works in job descriptions. And so we found that a lot of the ways that casing and some of the context and some of the pre-processing of these models works is actually not very great for some of the work that we're doing. And so it led us to this sort of question, this problems with the pre-trained models. And for you guys, it might not matter as much, but these were things that we sort of had to sort of go through and realize. The first is obviously abbreviations and words, and they matter differently depending on what your application is. In terms of out-of-vocabulary words, and we actually found that to be quite difficult. So one of the beauties of job descriptions, but also the difficulties of job descriptions, is that they're very incredibly domain-focused. And so they're almost like trying to compare theses of different disciplines a little bit. And so words that can mean something in some contexts mean very different things in other contexts. And so we're also dealing with the issues of domain-specific words that don't come up in the Google crawl very frequently, or not in the format that it would in a common sense. The other sorts of areas that we've had trouble with is in terms of multi-word expressions, so phrases that have new meaning. So front end is very different to front and end. And polysemy. So these are words that have multiple meanings. And for us, this is important because chef is a job, but it's also a language. And drive a car is very different to drive results. And we have car driver jobs in our database, and we have corporate jobs in our database where these are actually play important roles. And so what ends up happening is when you have words like this, your embeddings sort of, if you're using pre-trained embeddings, they won't necessarily reflect this corpus and some of the idiosyncrasies of your corpus. And so that's what I sort of wanted to highlight as a key issue. So we've had to train our own embeddings, and part of what I'm going to be talking about are some of the amazing tools that you can do that with and some of the new technologies that we've seen. So corpus processing wise, we use a lot of Spacey. We've basically forked our own version of Spacey right now because our own forms of dependency parsing and noun, like as in phrase extraction and things like that Spacey does very well. But there are a couple of other Obviously, I would be remiss to not talk about some of the others. The Core NLP has had some recent really impressive updates, and SyntaxNet, I think, is the new name for Google's Passface. And then on the other side of things, in terms of language modeling, these have become the thing that I love about it is the modularity. So, we use Spacey with various, depending on what the context is, TensorFlow or GenSim backend, but these are great in terms of they're very clean APIs for language modeling. They've all are being optimized to a point where they're running as fast as they possibly can using, the top NumPy and Pandas implementations. And I would when you think about distributed systems, SageMaker is probably one of the better ones in terms of the way that you would implement a language model, and it's something to consider. And so one of the things that I wanted to talk about is in terms of the parameter tuning. So when you roll your own, as you would say in the word embedding space, there's a bunch of these sorts of tunings that are actually really important. What we find is and this is again that toy example that I showed you earlier, when we train with a small window size, what we find is that you capture semantic similarities, and these are basically words that can substitute, versus when we train with a much larger window size, you get things like things that would be a little bit further away, things like statistical modeling and SPSS. These are all going to clump a little bit closer together with Python. And so these are going to be things that are alternatives rather than substitutes. And I'll talk a little bit more about alternatives and substitutes a little bit later, because actually that's something that I think is really interesting about this work. So when we trained our own embeddings, we've done a bunch of tests. This is one of the few tests. This is just an eyeball test, which is what most people do. But we've also done similarity tests and run a bunch of other sorts of algorithms on it. You can see that the equal opportunities language tends to cluster together. The perks language tends to cluster together. Obviously, there's a lot more equal opportunities in perks language. These are the top 500 words from our embeddings, just from a TSNE visualization standpoint. What we see is that soft skills, so things like problem solving, communication, also cluster together, which I thought was really interesting, because I didn't expect them to, and because in the context of a job description, they typically are sort of distributed throughout the job description. It's not always in a clean chunk like you would expect with the equal opportunities or the affirmative or the perks language. And lastly, in terms of just the talking about language about experience tends to cluster together, and maybe because we have got a lot of finance roles, that seems to have come up in this set, but in general, that was sort of very validating. So iChecks are one way of evaluating embeddings. There are other sorts of ways in terms of looking for word similarity, and we have those. We've basically had to build those algorithms. We have to build those systems too. So that's one of the problems with designing your own embeddings, because you can't take what's off the shelf and assume that it's going to work for you. You have to build the test to see which one is actually the best. But if you do an iCheck and you're okay with something that, this is again a distribution. This is so this is a dimension reduction algorithm, so you're not going to see everything in every dimension. There are issues with using this as your sole source, but that's something I can talk about later. So I have got 300, actually that was 100 dimensions, but time isn't one. So how do we look at the time course of embeddings? And one of the mechanisms is train a separate embedding on each time course and then stitch them together, right? And the second one, and this is actually done by quite a few groups, this is just a subset of the groups that do this. The second major mechanism is to train them all together. And these both have pros and cons. And I'm going to focus on the pros of this one and the cons of this one, because this is what we're using. The first thing is in terms of data hungriness. I think this is a much more data efficient algorithm, and I'm going to show you how we did it with 50,000 and 500,000 job descriptions. So that's quite small by way of a corpus, and we've been able to extract some very interesting signals. And the second is that this requires alignment. So just because we have a 300-dimensional embedding in each of the cases doesn't mean that you could figure out where experience is in this one and then map it to that one and that it's going to be in the same place. You actually have to stitch this experience to that experience and that experience. So you have to find the words that are constant between them, decide what those are, and then stitch them, versus the dynamic embeddings, which don't actually require alignment, what happens is that we're assuming that these are, because they're trained together, even if you have sparsity, say 2016 is a year that had fewer data science jobs, which actually didn't. But if it did, and we have fewer words, or say our corpus, say our server went down and we lost half of our corpus, you can still impute through that process because you're using some of the statistical information from the years before and the years after. So the implementation we used was, as I mentioned, by David Blei's lab, and that is because the other two groups over here did not actually publish or put their repos anywhere that we could find. So to academic researchers, if you put your things out there, someone will actually use them. And this is a repo link that we use. And basically what we found, and this is again results from their paper. So what they showed was using Senate abstracts. One of the outputs that I think is very interesting is the absolute drift. So what it does is it just gives you a text file of all of the words that show the most drift. And the second thing that it does is that you can take a word and then find the neighbors of those words in terms of find the neighbors of those words. So, unemployment was one of the top words here, and you can see how it changed from 1958 to being about something sort of moral, I guess, in this case. And then here we're talking about alleviating it, and then we're talking about how it becomes a very economic term in terms of forecasts and joblessness, and it's less of a moral term, so it sort of shows that distinction. One thing to sort of note here is that this is, we're talking about 140 years. What we were trying to do is map it over 3 years, which is, quite a lot different. And so we've, it was kind of a crazy project that we had, and so I'm going to show you how we did it and what the results were. So again, we did those in time slices. We're now actually experimenting with breaking down the time slices into a couple more time slices, so like quarters or half years. But our initial experiments were like sort of the number of documents. This just happened because we had a streaming error at one point and we couldn't get past the 50K mark. But we've now gotten past that, obviously, and have got a much larger corpuses, and we're scaling up to a 5 billion number of documents. It just takes a long time. We need more Amazon's server space to do this. We restricted the number of the vocab size. That's partly because that's what the original implementation did. And in general, most of these embedding models do restrict the number of the vocab size, and so what you end up doing is losing a lot of unique words. In our case, I think we were on the edge, and so we're actually going to experiment with that. And with data pre-processing, we didn't remove stop words. We did very basic data pre-processing. So words like New York were put together, or New York City was put together. But outside of that, it was sort of very simple and very straightforward. And that, I think, is the biggest thing, because this data pre-processing process can take a long time. We did the minimal in terms of all of that. For those of you who are very experienced with embeddings, you'll see that we trained embeddings with 100 dimensions. It's partly because that's what the group that published this had most success with. That's quite small. The Word2Vec embeddings are 300 dimensions, and so that's quite an order, quite significantly bigger. But actually, what we found with this was actually much stronger results for whatever reason. Okay, so actual results. First thing. When we trained with a small corpus, what we found was that in general we found gains and losses in skills and losses. So I showed you that initial documentation that said like the top words that came out of it, and one of the top words that came out of it were PhDs and MBAs, and our top 10 words. So when we went back and looked at our database, we saw that actually in the since 2016 to 2018, and these are the numbers that I'm going to show you, the number of jobs that require PhDs as a relative number of jobs has dropped, and same thing with MBAs. When we look in data science jobs, actually that effect has been stronger. And I know the people probably who are job seekers don't feel like this is actually happening, but I mean, we've looked across the board. Like, you think that machine learning and deep learning is all on the rise, but actually we didn't see that, and we certainly saw that like the requirements for PhDs are actually getting lower. Oh yeah, and then the other thing, so again, blue boxes are the phrases that were indicated from the top drifting words analysis. what we were surprised to find, I was expecting to see, honestly, when we did this project, I was like, SQL is going to be on the rise because I see it used in so many different types of Java. Actually, SQL was nowhere to be found even in the top 100 drifting words. What we did find, though, was Tableau came up a big one. So data viz in general was something that we saw in our jobs over the last 3 years has gone up in a big way. And actually, one of the things I want to look at is to see whether there are certain verticals where that's actually happening. But across all data science jobs, Tableau is doing well. Hadoop was something that came up out of our initial analysis, again in the top 10 drifting words, which I was surprised about. And what's interesting is I threw in Spark because I was like, I'm kind of curious, like, is it all of these sorts of processes or just some of them? And I think partly because my theory is that AWS instances have become much easier to deploy, that in most companies that sort of probably corresponds to sort of like, as in they'll remove the requirement for Hadoop. But Spark is still steady. And then the last thing is, and this was an obvious one, I mean, Perl came up. There are very few jobs that require Perl, but Perl is actually frequently required in combination with Python or in combination with Java or as an alternative. And actually, you know, it's dropped a lot. It wasn't starting off from a very high beginning, but it actually did drop a lot. And obviously, Python's steady. So Python actually didn't go up. In contrast to, I've seen a whole lot of reports about talking about Python in data science jobs and Python in general. I think we have a lot of Python practitioners, but I don't think that it's you know, the number of jobs that require it are going up that much. When we looked at a large corpus, what we did see were more subtle effects. And actually, I was super excited when I saw SQL in my list from the large jobs, because I was like, yes, finally. Maybe the small one made no sense whatsoever. And actually, when we go back and look at this, if we look at the number of jobs that require SQL in general across all jobs as a percentage of all jobs, what we see is no real difference in SQL demand. But what we do see is that in specific verticals, we're seeing increase in SQL requirements. So in FP&A roles, so these are finance roles, in biz dev roles, we're seeing an increase in SQL requirements, and in HR roles. And as someone who works in the HR space, for all of the people who are still looking for jobs, like, please go and join HR departments. They really need data analysts. They need people who know SQL, because this is a big area and it's really important in terms of opportunity and in terms of making sure that these processes are fair, because then we need people who can work with data in an effective way. What I found interesting is when we looked at corollaries, so in fintech roles or in sales or marketing roles, these are basically steady. So it is coming up in certain specific functions. And the reason why we had to do this analysis in this way and looking at the number of jobs in specific subtypes is because one of the problems with the repo is that some of this analysis is actually the directionality and what are the nearest neighbors is somewhat hard to extract. So we're still working on trying to get them to do that, help us with that. So what I talked to you about today was like a dynamic Bernoulli embedding. It's a subtype of a family of embeddings called the exponential family of embeddings. And the reason why it's called that is because it's thought to be in the same way that regression is to generalize linear models, we have word to vec as to this family of embeddings that exponents that applies probabilistic context to the data. And I'm going to show you a couple more examples and hopefully get you excited about how you can use it in some of your roles to end with. The first is we did all of this analysis using Bernoulli embeddings. Bernoulli embeddings, very good with binary data. So we're basically taking the word, the data point is the word and whether it exists or not, and the contexts are, again, whether those words exist or not. So that's sort of the context of why it's called an exponential dynamic Bernoulli embedding. Poisson embeddings are another type where you use count or ordinal data. And so what you would imagine, and this is very good for shopping cart analysis, so you would take an item in a shopping cart and then look at what other things has that person bought and what is the likelihood that they're going to buy this one other thing. And Gaussian embeddings are especially useful for continuous data. So in this case, I'm showing you what would be a graph database with nodes and edges, and the continuous data that I'm referring to is the weight of an edge given the other edges on the same node. So if we're looking at, I think in this case, this is a bit of a mixed up example, but if we're looking at New York as an input, how does this interact with, like, given these other contexts of other airports that come in and out? And what I think is really interesting about Poisson embeddings, as I sort of mentioned earlier, is that, you know, this, if you think about them in the word embedding space, you're like, of course, coffee goes close with orange juice. But if we abstract these into a bunch of numbers and categories, right, and which is what the original group did, and then through shopping cart analysis, and this was only hundreds of thousands of rows of shopping cart analysis, so it's actually quite small in terms of a training set. What they found was if you convert that back into the key that it was, you find that your Yoplait yogurt finds other Yoplait yogurts, and chicken ramen finds other types of ramen as well, which I thought was really fascinating in a totally unsupervised way, in a way where the numbers had no relationship to the words themselves. And so I think that was fascinating. The last thing that I think this is the last thing I'm going to talk about today, is that this lends itself to a couple of different things. The first is that by casting these in this probabilistic context and understanding the inner dot product, you can figure out things that have high inner dot products. So if we buy old Dutch potato chips, you have a high likelihood of buying a beer. And the same thing with if you buy Lay's potato chips, you're also really likely to buy frozen pizza. And it also yields things that are rarely bought together. And so what you can see here is, again, if you buy Tide plus detergent, you're very unlikely to buy Cinnamon Toast. And that's kind of interesting because it's like those are two things that are rarely bought together. That's fine. But it also yields things that are substitutes. So if you buy one type of soup, you're less likely to buy another type of soup. And so that's actually a very interesting, from a e-commerce sort of side of things, really interesting. It's also very interesting from a word perspective. So we can find words that can be substitutes, or skills that can be substitutes, and skills that are alternatives. And that's something that we're very interested in as a company that's trying to tell people, maybe you should think of these alternatives when you're thinking of jobs. So to conclude, I'm going to talk to you about the flavors of static word embeddings and the issue of corpuses, and how important they are in terms of when you're using pre-trained embeddings. In terms of custom embedding models, I talked about some of the considerations that you might want to apply when you're considering how to implement them. I gave you an example of a dynamic Bernoulli embedding and how we use that to understand data science skills, and how we showed that things like using a smaller corpus allowed you to figure out things that were either there or not there. And using a large corpus gave us very subtle detail about some of the skill sets, and the language as well of job descriptions, which I didn't have time to talk about today. And then the last thing that I talked to you about was just other families of this exponential family of embeddings, and the way that you can use them. And of course, I talked about dynamic Bernoulli embeddings in the context of, you cast the year's worth of the different types of embeddings across the years, right? But you could actually use that same intuition and do that across categories, and so create embeddings. And in our case, we're creating embeddings based on junior roles versus mid-level roles versus senior roles, and how do the way we talk about skills along the seniority spectrum change the way that they're talked about in job descriptions. So with that, I just wanted to thank you.